continuing. Here is the following theorem gives conditions under which a function is guaranteed to possess extreme values. The extreme value theorem. If f is continuous on a closed interval AB, then f attains an absolute maximum value Fc and an absolute minimum value Fd at some number C and D in AB. This is very important theorem. It says as long as your function is continuous and you are looking at a closed interval, you are guaranteed an absolute maximum value and you are guaranteed an absolute minimum value. Here are some examples. A to B. So you draw your function continuously, you are bound to hit a maximum, absolute maximum and an absolute minimum. Here is another example. You have a maximum here, but notice the absolute minimum is at the end point, which is okay. Here is another option. Aha, this and this, they both seem to be absolute maxima. This is the absolute minimum. All right. So an extreme value can be taken on more than once. Of course, here you have both places absolute maxima. All right. Now, a function need not possess extreme values if it is not continuous or if it is not on a closed interval. Okay. If either hypothesis is omitted. For example, here is somebody who is a discontinuous function. The function is defined from 0 to 2. At 0, it has height 1 and then it increases and that's an open hole, notice. Okay. And then at 1, you continue somewhere below. So because it's broken, you don't see an absolute maximum. That's a hole, that point. So because that point is a hole, there is no point there. There is no absolute maximum. All right. Now here is another option. If your interval is not closed, so the interval is closed here but open here. So my function actually has a vertical asymptote and it keeps growing here. So there is no absolute maximum. Next, the function f whose graph is shown. This is the description, explanation of what I just said. Let's continue. This is also the description of what I just said. Now, the extreme value theorem says that a continuous function on a closed interval has a maximum value and a minimum value, but it does not tell us how to find these extreme values. Okay, so what do we know from the extreme value theorem? We know that there is a maximum and a minimum, but we don't know how to find these maximum and minimum values. So here is an example. This is a local maximum. You notice the tangent? Tangent is horizontal. Here is a local minimum. You notice the tangent? The tangent is horizontal. Okay, so it appears that at the maximum and minimum points, the tangent lines are horizontal. That is, they have slope 0. We know that the derivative is the slope of the tangent line. So it appears that derivative must be 0. Okay, now, so this is a famous Fermat's theorem. Okay, Fermat's theorem says if your function f has a local maximum or minimum at C, and if the derivative exists, then it has to be 0. Okay, if you have a local maximum or minimum at C, either the derivative has to be 0 or the derivative should not exist. You understand? That's what this means. If the derivative exists, then it must be 0. Okay. Now, on the other hand, look at this. This is cube. At 0, the tangent will be horizontal, but it is neither maximum nor minimum. You understand? So, horizontal tangent does not mean you have maximum or minimum. But having a maximum or minimum, if you have derivative, then your derivative must be 0. Okay. Derivative equals 0 simply means the curve has horizontal tangent. Okay. Having a maximum or minimum at 0, 0, our curve x cubed crossed the line, okay, horizontal line, and that's okay. Okay, now here is another example, concrete example. So you have absolute value x. At this point, because it's pointed, you cannot find the derivative. Derivative does not exist. But notice this gave you a minimum, actually absolute minimum. Okay, even though derivative does not exist at that point. Okay. Now, oh, what happened? So we must be careful when using Fermat's theorem. If derivative is 0, you are not guaranteed maximum or minimum. Okay. You may have, secondly, if you have an extreme value, derivative might not exist like we saw in the absolute value function. So be careful with the Fermat's theorem. Okay. Which brings me to critical number. This is an important definition. Critical number of a function f is a number c such that either derivative is 0 or derivative does not exist. Okay. In other words, if you have a local maximum or minimum at a number c, then c is a critical number. What is a critical number? Derivative is 0 or derivative simply does not exist. Okay. So how do I find absolute maximum or minimum for any continuous functions? Here are the 3 steps you need. First, you need to find the critical numbers. You need to find the values of f at those critical numbers. Then find the values of f at the end points. Okay. And then the largest of all these values is absolute max. The smallest of these values is absolute minimum value. Okay. Now that completes the lectures for 3.1. I will upload these slides on Blackboard for your benefit. Okay guys. See you soon with exercises.